Okay, hi. So, welcome to this talk at TyphoonCon 2020. This is about analysis of DTLS implementations using protocol state fuzzing. This is a joint research effort by Paul Fitro-Brostein, Bengt Johnson, Juri de Ruyter, Konstantinos Zaganos, and Juraj Zamorski. And myself, of course. So let me introduce myself. I'm Robert Merget. I'm 29 years old. I'm a PhD student at Ruhr University Bochum in Germany. And my research topic is mainly focused on TLS and DTLS, and I do real-world crypto and dynamic protocol analysis. And I'm a main developer of TLS-Attacker, which is a framework I'm going to talk about later. And if you want, you can follow me on Twitter. I'm at icons1 with 0. So what is this talk about? So I guess most of you are familiar with the word fuzzing, so you spotted that in the title. So fuzzing is a concept where you send inputs to an application, so the system under test, and you hope that it crashes. And in the past, there have been several improvements to fuzzing to make the input generation better, to make the system under test crash more, or to improve the performance in general. And fuzzing is nice if you want to find classical programming errors like memory errors, buffer overflows, buffer overreads, undefined behavior, race conditions, and so on. But it's not so nice if you want to find logical flaws, which usually do not crash the application and are very application specific. So let me show you an example of such a logical flaw. This one is in libSSH. So in SSH, you first exchange versions, then you exchange some public keys. Then the client can send a service request message, which the server is supposed to answer with a service accept message. And then the client is supposed to send a user authentication request message, which basically contains a proof that the client is in possession of a secret the server uses to authenticate the client. And if the client is successful in providing the secret, the server is supposed to answer this message with a user authentication success message. And afterwards, the SSH connection is established and the channel can be used. But libSSH had an interesting flaw in 2018, and this flaw allowed an attacker to completely bypass the authentication. So what he would do is he would start the authentication process as usually, but instead of sending the user authentication request message and receiving the user authentication success message, he would instead send a user authentication success message himself, and this bug caused the server to think that by this miracle, the user is authenticated, although the user did never provide proof that he actually knows the secret key. And this is obviously a disaster, and these kinds of bugs is what this talk is about. Because with state machine fuzzing, you can find these kind of bugs autonomously, and this is what we are going to do today. So this is the big picture of state machine fuzzing. So we have a system under test, so some piece of software we want to analyze. When we will apply state machine fuzzing to that piece of software, and we will extract some kind of model. When we will use our expert knowledge to analyze this model, and then hopefully find some bugs. So let's talk about the system under test first. So I'm a TLS person, so it's naturally for me to talk about TLS or DTLS. And I guess most of you know TLS. It's a protocol behind HTTPS. And if we talk about TLS, we often show this picture. So this is the TLS Handshake. And in the TLS Handshake, the client sends a ClientHello message containing a list of supported client features. The server answers this message with a server hello message, where he chooses the parameters of a connection. He sends a certificate message, and then he sends a server hello done message telling the client, hey, okay, I'm done talking, it's your turn. The client follows it up by a client key exchange message, in this case containing maybe the encrypted pre-master secret or the public key, followed up by a chain cipherspec message, which tells the server, okay, my following messages are encrypted, you have to decrypt them, followed up by a client finished message, which is a HMAC over the transcript of a message exchange. So basically a checksum for the server. And the server follows this up by a chain cipherspec and finished message himself, telling the client, hey, I'm going to encrypt my messages as well now, and here's my finished message. You can check that the connection has not been tampered with. And afterwards, the connection is established and the application data can be exchanged. So this depiction is often visualized in textbooks about TLS, But this is actually not the whole truth. So TLS is actually a little bit more complex. So there's this thing called extensions, where client and server hello can contain extensions which alter the cryptographic computations, but they can also change the messages which are exchanged. Then there's this thing called ephemeral ciphers, where the server also has to send a server key exchange message. It's to provide fresh key material to the connection. Then there's this feature called client authentication, where the server can request that the client also authenticates by sending a certificate request. The client then has to answer this with a certificate and a certificate verify message. Then there's this thing called renegotiation, where a new handshake is started after the first handshake has already been started to exchange new or to negotiate new parameters for the connection. This might be, for example, if you have some top secret part in a website which needs stronger keys, then you can renegotiate the session to get stronger ciphers. Then there's this different messages which are added due to different TLS extensions. For example, the certificate status message can be added to staple or to send a UCSP response within the TLS handshake, or the famous heartbeat protocol, which can be used after the connection has been established. And also, I lied a little bit. The certificate message is actually not mandatory, so it's actually an optional message. So some ciphers do not require you to send a certificate message. And then there's also this thing called session resumption, where you exchange this message order quite a bit, and you drop a lot of messages to get a shorter handshake and a faster connection established. And this is not everything. So there's also TLS 1.3. And TLS 1.3 changed the message order quite a lot. So now the exchange looks completely different. And TLS 1.3 also has a feature called zero RTT, where the client can actually send application data with its first ClientHello message or its second hello transcript, second hello exchange. And this has also been ended by end of early data message. But then there's this thing called, then of course the server also has to skip some messages. But then there's this thing called compatibility mode, where the client and the server both decide to send chain cipherspec messages which are ignored by both parties. So what's the deal with that? So the idea is that there might be a firewall in the middle which only talks the older protocols, so you try to trick it into thinking that this is actually not a TLS 1.3 connection, but a TLS 1.2 session resumption. And with that not enough, there's also this thing called hello retry request. So in TLS 1.3, the client guesses the group that is used for the connection, and if he gets wrong, he has to retry the connection. And this also contains those chain cipherspec messages, and is followed up by the normal connection afterwards. I did not talk about TLS 1.3 client authentication or TLS 1.3 rekeying or TLS 1.3 session tickets, but you can already see that this gets quite complicated. And we only talked about TLS so far. There's also DTLS, but let me introduce DTLS really quickly. So DTLS is TLS for UDP. So UDP does not guarantee you that the messages are arriving in order, that they do not contain bit flips, and it also does not contain a guarantee that the packets actually arrive at the destination. So DTLS also has to work if packages get lost, reordered, retransmitted, or contain arbitrary bit flips. Additionally, DTLS has some additional denial of service protection, since it's very easy to spoof IP addresses in UDP. And it also has some additional fragmentation options, since in DTLS, in UDP, there's the maximum transmission unit, and it's usually much smaller than in TCP. So it's usually necessary to fragment the messages more. And to deal with retransmissions, DTLS contains a sequence number in each handshake message and in each record, so that you can actually reorder the messages. And it also has some additional identifier to tell with which keys you have to decrypt a specific message. This identifier is also called the epoch number. Okay, so the DTLS handshake looks very similar to the TLS handshake, but additionally there's an additional exchange at the beginning. So you first send a ClientHello message, then the server answers this message with a hello verify request message, and this hello verify request message contains a cookie, and the client is then supposed to retransmit this cookie in a ClientHello message to prove that he's actually able to receive data on this IP address. And afterwards the exchange is basically identical. So let's talk about the implementation of a state machine here real quick. So if you are a DTLS implementations, you always have to know which messages you are supposed to send at which point in time, and which messages you are allowed to accept at which point in time. So it might be that you receive an out of order messages and you have to think, oh, am I actually allowed to receive this now, or do I have to discard this? And how do you react if you receive an unexpected message? So what if the client is not following the protocol and he's doing something completely different? And as I've hopefully convinced you, this can get quite complex, especially if you have retransmissions, dropped messages, and maybe bit flips in your messages. And the proper way to implement this as a Mealy machine, which is basically a state machine. And let's talk about that real quick. So if you are back at the big picture, we'll talk about now about the model, which is the Mealy machine. So I guess some of you probably know Mealy machines already if you study computer science or something similar. It's those graphs here you see here, yeah. And a Mealy machine consists of states. Those are the circuits, so there are different states in a Mealy machine. And there are transitions, so you can move from one state to another state with those transitions. And the text above those transitions tells you basically the input and output required to move from one state to another. So 1 on the left side is the input, and this tells you if you are in state S2 and you want to move to state S1, you have to send a 1, and as an output you will get a 0. Yeah. So this is just a basic example here. And semi-formally, a Mealy machine consists of the following things. So there's a finite set of states, so the number of states in the machine is not infinite, and is actually predetermined. Then there's a set of possible inputs, so a set of possible outputs, so we know what the implementation can output. Then there's a transition function and an output function, which basically tells you the text above the transition. So for which, from which state you can go to which state and which output you will get and which input you will require. And then there's some starting state, Q0. So you have to start somewhere in this Mealy machine. So back to our example. This Mealy machine, the Q, so the set of states is S1, S2, S0. So this is basically just the circuits here. The input alphabet is all the possible inputs we can send, and this is basically all the possible text you can have on the left-hand side of the text. And this, in our case, is just a 1 and a 0. Then there's a possible output alphabet, so this is all the text on the right-hand side, and in our case, this is also just a 1 and a 0. And then there's the state transition function, which basically tells you how you get from one state to another. So if you're in state S0, you send a 1, you can move to state S1. And if you're in state S0 and you send a 0, you can move to state S2. And the output function basically tells you if you're in state S0 and you send a 0, you get a 0. And if you're in state S0 and you send a 1, you get a 0. And in this example, we just arbitrarily start at state S0. Okay, so I guess this is very clear, this is very basic. But now let's talk about state machine fuzzing. So how do we get such a model out of some arbitrary piece of software? Okay, so we want to extract a Mealy machine out of this arbitrary piece of software, but this can get quite complicated and we do not know how to do this yet. So let's talk about the things we already know about the Mealy machine. So do we know which states are in the final Mealy machine? or how many or something. And actually no. So for an arbitrary piece of software, we do not know how many states will be in the state machine. The next thing on the list is the set of possible inputs, also called the input alphabet. Do we know something about that? And actually, yeah, we can define something here. Like we can imagine that if we want to extract the state machine of a TLS implementation, we can say, oh, the inputs are the messages we're going to send. So the ClientHello, the change cipher spec, the client key exchange, and so on. And the set of possible outputs, yeah, we can also do something like that. So this is just the responses the implementation will give to us. So we can define the different answers from the implementation we can get. Then there's the transition function and the output function. We obviously don't know those. So if we would know those, we would know basically all the other answers. So those are unknowns to us. And the starting state, yeah, kind of. We can define some state where we start. So, but the rest is basically unknown to us. So let's talk about the input alphabet. So if we want to learn the state machine of TLS or DTLS server implementations, we can actually use the pictured input alphabet. So the input alphabet is basically an abstraction of the messages we are going to send. In this case, we chose the ClientHello message, the client key exchange, and cipher spec and finished message. And for those, you already have enough messages to actually learn a complete state machine which finishes the handshake. But we also added additional messages like the application data message, and the certificate and certificate empty message. So basically a certificate message with a certificate and one without one. Certificate verify message, and with those we could also already learn implementations or fuzz implementations which also require client authentication. And then we also added the two alert messages, one with a close notify and one with an unexpected message. But basically you can choose this input alphabet arbitrarily, so it's up to you how you want to define this. We also included different variations of the ClientHello and client key exchange messages with different key exchange algorithms. This allowed us to learn the implementations for different key exchanges, so maybe the implementations behave differently on different key exchanges. So as the output alphabet, you basically choose an abstraction of all the answers the server can answer with, or the system on a test can answer with. And you do not need to know this from the start. You can actually generate this as you go. But it's actually not so hard to determine this beforehand. So this basically server hello certificate message, server hello done, and so on. And maybe some special output symbols, for example, could not decrypt, or I don't know what this is, and stuff like that. Okay, so the state machine fuzzing process from a very, very high level view is that we have some piece of software and we have to generate a Mealy machine given this piece of software, the input alphabet and the output alphabet. So how we will do this is we will start with an empty Mealy machine, so that's basically just a starting state, and then we will try to improve this model. So we will try some message sequences such that this model better models the actual software. And if we are confident that our model somehow works and that's good enough, we will move to the testing stage where we will try to test the model and check if it actually behaves the way the software actually behaves the way the model predicts. And if this test fails, so the software actually does not behave as the model describes, we will try to improve our model a little bit more. And then we will move to the testing stage again. And if this testing stage is completed, we can just output the generated model. So let's zoom into this part here real quick. So if we want to learn state machines, there are different components. So there's the system on a test, which is basically the software we want to test. Then there's the mapper, the learner, and the teacher. The learner is just is a machine learning algorithm which generates input sequences which should be sent to the system on a test. For example, it can say, hey, we want to send a ClientHello message to the server, But the learner, this machine learning algorithm, does not know anything about TLS and does not know anything about DTLS either. It just knows basically the strings in the input symbol. So it just knows ClientHello. And it needs somebody to translate this abstract symbol into the actual byte sequence we can pass to the system under test. And this is the job of the mapper. So the mapper translates the abstract symbols into byte sequences, and he does this also the other way around. So if the system under test answers with some bytes, it translates this into an abstract representation so that the learner can actually deal with this. And the learner will then come up with different sequences of messages which should be exchanged, and the mapper translates them and tells the learner how the system behaved. And after some time, the learner will maybe send a finished message, maybe get an unexpected message, and after some time, he will come up with a state machine, magically. And he will then pass this model to the teacher, and the teacher is basically also some kind of equivalence testing algorithm. So it's usually also some machine learning algorithm, but it does not have to be such a sophisticated one. And the teacher then also tries different message sequences and tries to check if he can find a counterexample to what the model tells him how the software should behave. So he basically goes different paths through the graph, through the Mealy machine, and tries to find a contradiction. And if he finds one, he tells the learner, hey, I found a contradiction in this example ACA. I should get different responses due to, if I believe the model. And then the learner can try to improve his model again and can try to refine it. And if he's confident again, he can pass it again to the teacher. The teacher can check the model again. And if the teacher cannot find a counterexample, he will output the model. So this is the high-level flow. And for the algorithms used to generate the actual message sequences, we have quite a few. Most prominently the L-star algorithm or the TTT algorithm. And those are machine learning algorithms, but those are not the kind of machine learning algorithms you think they are. So they are not those with the neural networks, but they are really, really smart state machine learning algorithms. Okay, so now let's talk about DTLS state machine fuzzing. So what we did is we used this technique of state machine fuzzing for DTLS server implementations. So, and if you want to do this, we need to instantiate the primitives. So we need a learner, we need a mapper, we need a teacher, and we need a system under test. As a learner and teacher, we used LearnLib, which is a framework for automata learning, so Mealy machine learning or other automata learning. And it implements various algorithms which you can use for your projects. So for learning, we use the TTT algorithm, and for equivalence testing, we use the VP and VP random method. And you do not need to know anything about how these algorithms work internally to use them. So this is actually quite nice. You just have to talk to the interfaces. LearnLib is developed by the Technical University in Dortmund in Germany. That's actually just 50 kilometers from here, so it was actually quite nice to use this library, and it's actually quite mature. So if you want, you can check it out. The link is below. And for the mapper, we use TLS-Attacker, and TLS-Attacker is actually our framework developed by our chair. And TLS-Attacker is a flexible TLS framework which allows you to access the different aspects of the TLS stack very comfortably. So you can send arbitrary messages in an arbitrary order at an arbitrary time. And you can use TLS-Attacker also as a library to control the TLS stack, to have a custom TLS stack which you can control from another application. And this is actually what we did in this project. So we developed a new state machine fuzzer and used TLS-Attacker as a library. TLS-Attacker supports over 300 cipher suits and supports all the TLS and DTLS versions. Supports client, server, man-in-the-middle support, and it already found a lot of vulnerabilities in all the different TLS stacks. And if you're interested, you can find this project on GitHub. It's open source. I have a link below. And as a system on a test, we used basically all the different DTLS server implementations. So we had quite famous ones like OpenSSL, JSSE, NSS, GNU-TLS, but we also used some lesser known ones like PionDTLS, Scandium, TinyDTLS, to get the whole picture of the DTLS ecosystem. And to analyze the system on a test, we use different configurations like with and without client authentication. And also we use different key exchange algorithms in those implementations. So, and with that, we were able to extract the state machines. Here's a table directly from our paper, which gives you some idea of statistics about doing this. So, maybe interesting in this is the columns on the right-hand side, so the number of tests we had to execute, so it's basically in the 10,000s, and the time it took us to do this, so this is 3,500 minutes, or here it's a few hundred minutes. So it's actually quite a lengthy process, and the reason for this is that you never know if the other part is actually done transmitting messages, or if it's actually just computing something and responding later. So you always have to wait a certain amount after each message exchange. Also interesting is this column here, which tells you the number of states in the state machine. So the toy example I showed you before had like 3 states, but these examples can have up to 66 states, which is quite a lot and makes the whole analysis process very complicated. So now that we have some models extracted, we can apply our expert knowledge to analyze this model for bugs. So how does our expert knowledge look like? So this is basically it. So our knowledge above how the TLS handshake or DTLS handshake has to look like, how the implementation should behave, now should tell us if there are transitions or states in the state machine which should not be there. So let's look at some bugs we found. This is a state machine extracted from PionDTLS, and its client authentication was set to required, so it was enabled. And what I did here is we colored the transitions which follow the correct handshake in blue. So if you would send those messages, you would get to the usually supposed executed handshake. So in this example, you send a ClientHello, you get a hello verify request, you send another ClientHello, you get a server hello certificate, server key exchange certificate request, and server hello done message. Then you send a certificate, then you send a client key exchange message, get no answers for both. Then you are supposed to send a certificate verify message to prove that you're actually in possession of a private key. And afterwards you are supposed to send a CCS message, still no answer from the server, but then finally if you send a finished message, you get a CCS fin, and the connection the channel is established and can be used. But as you can see, there are 2 additional states which we did not visit yet, so there's state 7 and state 10. And you can get to state 7 if you send, after the client key exchange message, you send a CCS message. So you are supposed to send a certificate verify message, but instead you send a CCS message. And this is fine for the server, and you can actually go back to the valid path by sending a certificate verify message afterwards, and then you can finish the handshake with a finished message. And this is definitely not wanted, so you are not supposed to exchange the order of these 2 messages here. But it's actually not tragic, because you cannot exploit this behavior. But there's also another path, which is this path from state 4 to S10, state 10. And what you do here is, instead of sending a CCS message after you send the certificate verify message, you just immediately send the finished message. So you basically skip the CCS message. And you get a CCS and finished message as a response, so basically the channel is completely functional from now on. And you can send application data and receive application data. You can also send the CCS messages afterwards, and you go back to state 8. This is a quite interesting bug, because if you do not send a CCS message, you are basically transmitting the finished message unencrypted. So let me show you how this looks like. So this is the exchange, how it's supposed to look like. I removed the client authentication since it does not play a role in this. And I will now show you the epoch numbers. So we can drop the change cipherspec message, and then our epoch numbers look like this. So the epoch numbers basically tells you with which keys the messages are encrypted. So the ClientHellos and all the messages up to the client key exchange message have epoch 0, so they are sent unencrypted. And usually after the change cipherspec message, the epoch number is set to 1, so the messages are encrypted. But if you do not send a change cipherspec message, your finished message does not get encrypted, and the server is still fine to accept this message and answers normally. And if we somehow manage to do this, we can also send application data unencrypted, and the server is accepting that. And sending unencrypted application data is obviously bad because it's also not authenticated, and bad things will happen if you do this. So what we did is we analyzed this bug, so how the server behaves exactly. And what we tried is we tried to send a change cipherspec message, but still send the application data message with epoch 0. So the application was fine accepting application data with epoch 0 before. So maybe if we send a finished message still with epoch 1, we might still be able to trick the application into accepting those messages. And this was actually completely fine for PionDTLS, so PionDTLS accepted this message. And this is obviously bad because this allows an attacker to inject arbitrary plain text into any DTLS connection at any point in time. So you can imagine, like, you can just drop some data within the data stream of a connection. So this was quite bad, but this was also fixed very fastly by the developers. And PionDTLS is also just a smallish implementation. It's not a very commonly used implementation. Here's another one. So this is JSSE, the unedited model. And as you can see, this looks terrible. Like, this looks just awfully complex. And I spent at least a day or two looking at this model and trying to find bugs in it. And this is if state machine learning goes south. Like, if implementation itself does not have a very good state machine model, they usually accept a lot of messages in the wrong order and behave very weirdly. And this can result in models like this. I'm not going to analyze this with you, and you do not have to read this, but I have an edited version which removed a lot of the stuff we do not need for this analysis. And again, in blue, I showed you the paths you should go if you follow the transcript. And in red, there are some bugs within the application. But I'm not going to talk about this in the model. Instead, what I'm going to show you is I'm going to show you a simplified view with a message exchange. So the bugs we found became prominent as CVE-2020-2655. And these bugs actually allow you to bypass client authentication within JSSE. So within all, if you do not know, JSSE is the default TLS implementation in Java. So if you're using some Java implementation and you want to establish a TLS connection, you're most likely using JSSE. Okay, so this is how the exchange is supposed to look like if you're using client authentication. So you send a ClientHello, hello verify request, ClientHello, then you get serverless certificate, certificate request, serverless done. And then the next block is very important because you're supposed to send a certificate, then a client key exchange message, then a certificate verify message, followed up by a change cipherspec message, followed up by a finished message. And afterwards, the server is supposed to send a change cipherspec finished message and this change is established. And the certificate verify message plays a crucial role here because the certificate verify message contains a signature of the past messages with a private key of a certificate. So it's basically the proof that the client actually knows the private key. The certificate is public knowledge, it's transmitted to plain text, so everybody can copy it and paste it into their messages, but only the person with a private key of a certificate is supposed to authenticate with that certificate. Okay, so let's go to the bugs. So the first bug is in the DTLS stack. which we analyzed, but we also checked if it's also present in the TLS stack. So most implementations have both support for TLS and DTLS, and they often share a lot of code, so we tried to see if we could pull off the same exploit for TLS as well. And in this case we were able to do so. And what we did is we just dropped the certificate and certificate verify messages. So the server asked us to send a certificate and authenticate, and we just don't. We just follow the protocol as if he didn't ask for that. And JSSE was actually quite fine with that. So if we do so, the handshake terminates and we can exchange application data as usually. But there's a catch to that. So if the application using JSSE actually wants to see who authenticated, and is not just fine with somebody who is allowed to access the resource, then there will be an exception, and a PR authenticated unverified exception is thrown, because we did not send a certificate, and in the internal state of JSSE, the variable containing our certificate is null, and this causes the exception to be thrown. So this is not well already, but it's actually not good. So you may wonder where you can use this exploit. We're actually able to pull this exploit off with Apache Tomcat. So you can configure Apache Tomcat to use client authentication and JSSE, and if you do so, you can bypass the authentication by just not sending a certificate and certificate verify message in a vulnerable JSSE version. And then there's another exploit, so this one is DTLS only. So what we do here is we send a certificate, but we change the order. So usually we are supposed to send the certificate first and then a client key exchange message, but this time we exchange the order and we drop the certificate verify message. So we do not send the proof that we actually know the private key for the certificate. And this, interestingly, if we would change the message order, it would have not worked. So certificate client key exchange does not work for DTLS. And if we do this, so this time we send a certificate, the certificate inside the JSSE state is not null, and therefore no exception is thrown. So this is actually undetectable by the application, and we can actually authenticate as anybody we want to, as long as we have a certificate for that user. Another bug, this one is TLS only, and this is basically very similar to before, but this time we exchanged the certificate and client key exchange message back to normal. So we just drop the certificate verify message. This does not work for DTLS, but it works for TLS, or worked for TLS. And similar as before, we do not verify ourselves, we do not prove the possession of a key, and therefore we are bypassing the authentication. So, the side note, Oracle thought this was very hard to exploit. I would say no, because you're just commenting out one line, the send certificate verify function, and you are done with your exploit. You have a fully functional exploit. So, but oh well. So this was quite bad and actually quite easy. But we got another exploit which is quite complicated, and let me show you this one. So this one is DTLS only. So we start off like in the first exploit, we just ignore client authentication for now, we just send a client key exchange message. We followed up a chain cipherspec message, and then usually you're supposed to send after chain cipherspec message always a finished message, but this time we send a certificate message, which is quite odd, when we follow it up by a finished message. And when we follow this finished message up by another chain cipherspec and another finished message. So when I saw this, I was like, what the fuck? So what's going on here? And the reason this exploit works is actually quite funny, at least in my eyes. So we start off with a client key exchange message, which is already a violation of a protocol. So this is basically the first bug we found. And when JSSE is looking for a encrypted chain cipherspec message and an encrypted handshake message, it does not know that the encrypted handshake message is not a finished message without decrypting the message first. So what it does is it moves the state machine forward because it sees, oh, I got a chain cipher spec and an encrypted handshake message, an encrypted certificate message. And when it's decrypting the messages, it sees the certificate message and then it says, wait a minute, this is not a finished message, I'm in the wrong state, and moves the state machine back to the previous state. And in this previous state, it's looking for a chain cipher spec message and an encrypted finished message again. So what it sees afterwards is it sees the encrypted finished message and it's like, okay, this is a finished message. I want a finished message, but I do not want it now. I want a chain cipher spec message first and a finished message, encrypted handshake message. So it adds it to the buffer where the certificate message is already in. And then it sees a chain cipher spec message and another encrypted handshake message, and then it's like, yeah, exactly the messages I wanted, and it starts processing the messages. So it starts to process the certificate message and adds the certificate message to the current state. And when it sees a finished message, it's like, oh, a finished message already, so we have to be in the end of the handshake, and the finished message is valid, and it just drops all the other messages afterwards. So the chain cipher spec and finished message are actually not processed by JSSE, and it thinks the handshake is actually already completed. So now that I showed you the exploits, I will now show you a demo of those exploits. Let me move to the demos section. So I'm turning off the camera for now. Okay, so here you can see basically 3 shells. So on the top left side we have a vulnerable JSSE server running TLS. On the bottom left side we have a vulnerable JSSE server running DTLS, also on port 4433. On the right hand side we have TLS-Attacker. And TLS-Attacker ships with some example scripts which allow you to execute various protocol flows. And for this, TLS-Attacker uses the concept of workflow traces. And a workflow trace is basically an XML file which tells TLS-Attacker what to do. And I'm going to show you this on the first example. So this is the first exploit. So what we do is we want to send some messages. We want to send a ClientHello message. When we want to receive messages, to receive a server done message. When we want to send a client key exchange message for whatever ciphers the server chose. And then we will follow up by a change cipher spec and finished message. Note that we do not send a certificate or certificate verify message here. And when we will receive messages, so this will be the change cipher spec and finished message from the server. And when we will just print out the last seen application data. If we want to execute this trace, you can just run TLS-Attacker. So there's this example tool called TS Client, which basically can load those workflow traces. And we say connect to localhost on port 4433, and as a workflow, you run TLS exploit1.xml. And if we press enter, TLS-Attacker will execute this workflow trace. And on the right hand side you can see here what's happened. So we sent the message ClientHello, and then we received a server certificate, elliptic curve diffie hammer ephemeral server key exchange message, the certificate request, and the server done message. Then we send a client key exchange message ourselves, a chain cipher spec, and a finished message. And we received the chain cipher spec, finished message, and we received application data. And the application data actually reads hello CVE-2020-2655. So this is obviously bad, and from Fuzz's perspective we can see what happened. So the handshake completed successfully, and actually you are not supposed to successfully complete a handshake if you are derailing the message sequence. The connection is valid. The client authentication was set to required. But if we want to access the peer certificate, it is detectable that peer is not authenticated because this exception is thrown as a peer unverified exception, peer not authenticated. So if you do not access this, the connection is completely valid, and you can actually send application data through it, shown by the receiving of hello CVE-2655. Okay, so this was the first exploit, and now let me show you the second one. So this is basically the second exploit, which works for DTLS only. And what we do here is we send a client key exchange message, and then we follow it up by a certificate message. So we exchange the order, and we skip the hello verify request message. So if I want to send this to the server, I have to start as before. So connecting to localhost. But now I have to tell it to use UDP and to use DTLS. So what I do is I say transport handler type UDP. And we set the version to DTLS 1 or 2. And we load the workflow trace in. And we also need to load the certificate we want to send. So we have to send a valid certificate. We do not need the key for this, but we need to have a valid certificate. And firing it up. Okay, so here's what we can see. We send a ClientHello message. We got a hello verify request. We send another ClientHello message. We got we use the serverless certificate, elliptic curve TVM, and server key exchange message. Certificate request and server hello done. And we followed up by elliptic curve TVM and client key exchange message, followed up by a certificate, skipping the certificate verify messages and sending those messages out of order. And following up with a CCS and fin message. And the server is actually responding with chain cipher spec, finished, and application data message. And as you can see, it actually responded with 2 chain cipher spec messages. This is because they actually responded with chain cipher spec finished, chain cipher spec finished. But one of the finished messages is actually a retransmission. He does this on purpose for reasons not so important for now. And we can see he also was able to transmit application data, Hello CVE-2020-2655. And if we're looking at the server's perspective, we can actually also access the peer certificate. And he printed it here for us in the console. So from this point on, the application has no chance to detect which we actually not really authenticated. So next exploit, TLS exploit number 3. So what we do here, we just exchanged the order back to normal. So we send a certificate, we send a client key exchange message, but we just dropped the certificate verify message. And if we load this up, let me disable UDP and DTLS again and select the correct workflow. And let me restart the server real quick so we get a fresh console output. Okay, it's fired up. Okay, so we send a certificate, we send a client key exchange message, we do not send a certificate verify message, and JSSE is completely fine. We're finishing the handshake with us and sending us application data. And from JSSE's perspective, we can also see that we can access the peer certificate, no exceptions thrown, and the application has actually no chance to see that something fishy is going on. Here's the certificate I sent, I printed it on the console, and the connection is completely functional and there's no way to detect this. So, last but not least, the last exploit, DTLS exploit 4, and in my eyes the most crazy exploit I've ever seen. I can imagine if you are a competent pen tester, you can maybe also find the other bugs with TLS-Attacker, but I'm pretty certain that you cannot find this message sequence, because if you alter this message sequence besides the last finished message to another encrypted handshake message, just a slightly bit, you are not successful in the authentication step. Okay, so this is the handshake. We send a client key exchange, send cipher spec, certificate finished, send cipher spec finished, and hopefully magically we will be authenticated. So fire it up, exploit number 4. And as you can see, we send ClientHello, hello verify request ClientHello. He sends us usually a bunch of messages. We send a client key exchange message, change cipher spec, certificate finished, change cipher spec finished, and boom, we are authenticated. The server is sending us application data, and we can also access the certificate from the server side. Okay, let's move back to the presentation. So in conclusion, what we did is we were the first to apply protocol state fuzzing to DTLS, and we were able to find some critical vulnerabilities, especially the JSSE one is quite hard because JSSE is often used in government applications where smart cards are used to authenticate users, and this is quite dangerous there. Luckily, Java 8 was not affected and only affected Java 11, 12, 13, I think. And the technique seems obviously underused because protocol state fuzzing was already done by Yuri Ruta in, I think, 2015. And since then, obviously, nobody used this because he would have found the TLS bugs in JSSE. Like we did DTLS state fuzzing, we did not actually look for the TLS bugs. So this is quite bad. But I think protocol state fuzzing is actually quite a nice technique to have as a bug hunter or a penetration tester. So you should definitely have a look at that. And what's left to do is we need more automation. So this was just another one-shot research effort by our team. It would be nice if we could do this regularly to monitor the TLS implementation, since they also add new code and introduce new bugs, so we can find those bugs more quickly. So, questions. Due to different times, since I'm in Germany, so it's probably like 4 in the morning here or something. I cannot answer your questions directly, but I really want to answer your questions. So if you have any questions in regards to anything in this project, TLS, TLS-Attacker or something else, please contact me. You can either do this via mail or Twitter. I'm at icons1 on Twitter, and my mail is below. And if you want more details, the paper will appear at Usenix 2020, and it's actually online now. So you can read up on it and discuss some more bugs and some more details on how exactly we performed this. And with that, I hope to hear from you, and maybe I will see you next year when this corona pandemic is over. Bye!